In mountaineering, there are various scenarios where two ropes need to be connected. For example, for rappelling with half ropes when the full rope length should be used, or in mountain rescue maneuvers with a rope extension. I am Florian Hellberg from Edelrid Knowledge Base, and today I want to explore which knots are best suited to connect ropes. The discussion about which knot is most suitable is an old one, and different knots are taught in different countries. One option is the overhand knot, the figure 8 knot, or the double fisherman's knot. The first thing that's naturally interesting is what kinds of loads we actually encounter when abseiling. We want to look into this question first. So, about our measurement setup, we have attached the force time measurement point to the fixed point above, to measure the loads acting on the fixed point. Then we have attached the double rope here. Here below is my rappelling device. I have intentionally made a small loop here to deliberately sit roughly into the rope and see how much load then reaches the fixed point. Now I'll test a bit of sudden drop again. And now I descend evenly. The curve shows the force time progression of an 86 kilogram person who is rappelling with an 8.9 millimeter rope in double strand. The force shown is the one acting on the redirection. The first peak was caused by the sudden sitting. More sudden than usual when rappelling. The peak lies at just under 2 kilonewtons. The next peak occurred due to the sagging when lowering and is approximately 2.5 kilonewton. After that, during the steady descent, the force averages around the body weight. It goes slightly above and slightly below, but on average it is 86 kilograms. In summary, one can say that if you rappel very roughly, the forces during rappelling can be in the range of 2 to 3 times body weight. However, they only act for a short period. During moderate abseiling, the forces on the redirection are approximately at the climber's body weight. That means a knot that does not break at 5 kilonewtons, or does not roll beyond the rope ends, and does not start to roll at 2 kilonewtons, offers enough safety reserve even for a 120 kilogram person being lowered on a single strand. The usual practice will be that I rappel with a double strand. And that means, even with a 120 kilogram person, the knot is consistently subjected to 0.6 kilonewtons, or 60 kilograms, and at the peaks about 2.5 kilonewtons. Here we are in the laboratory at the static tensile testing machine. You can see here, one end of the rope is fixed in the machine, the other on slinging discs, so that we don't weaken the rope in the fixture. And in between, we now have our rope connection knot that we want to test. In a moment we will start the experiment, then the right sheave moves away and essentially pulls, applying the load to the knot, and in the measuring cell we measure the load currently on the knot. So you can clearly see here with the overhand knot that it first tightens a bit and then starts to roll, then alternates tightening and rolling until it completely comes undone. In contrast, the figure 8 knot starts rolling a bit earlier, but then tightens so strongly that it is loaded up to the maximum tensile strength of the rope, and the rope breaks. With the double fisherman's knot, you can see that it doesn't start rolling at all. It keeps tightening until the maximum tensile strength is reached and the rope breaks. Here in the overview graphic, we now see the values with an 8.9 mm dynamic rope for an overhand knot, a figure 8, and a double fisherman's knot. This means that our formulated requirements, even for a 120 kilogram person, of no slipping under 2 kilonewtons and strength, or no rolling out under 5 kilonewtons, are met by all 3 knots. Now, in addition to the strength requirements, there are also handling aspects worth considering. For handling and for safety during rappelling, an important aspect is that a knot should have minimal tendency to jam. One can see here that knots that stand up have the property of gliding better over edges than knots that run synchronously around the rope. Regarding hanging in cracks, a knot that's as small as possible is advantageous because it is less likely to jam. We have now illuminated the requirements and the advantages and disadvantages of the individual knots for connecting ropes in the segment. In the end, it is not only the choice of the knot that is crucial, but also the tying of the knot. So a knot must always be laid parallel and should not have any crossings. Needs long enough ends and must be tightened on all 4 rope ends. If I have concerns that my overhand knot will roll out of the rope, for example, because I'm knotting very smooth, impregnated ropes together, or want to lower very heavy loads, then I can secure the overhand knot with a second hitch. The second overhand knot secures the first from rolling out. It then rolls onto the second overhand knot and tightens until the breaking force is reached and the rope breaks. Anyone interested in the values for other ropes or for connection knots of ropes with different diameters can find the values in the article on the Edelrid knowledge base.